Okay, so there won't be, okay, so I'm the only one here. I'm sharing the screen. I put these two files are online. And just remember that, okay, so I'm going to post a quiz for you, I think tomorrow. And then you have an assignment which is due, I forgot, it's like in a few days. I forgot, I should have checked the time, but I put some hints on last night, but I encourage you to start it. Okay, so last week we talked about complexity, and we talked about like upper bounds and lower bounds. A lower bound would be like the best case scenario. Like let's just go through this, and we'll look at some examples here. So I just want to do more of that. The thing that we're mostly worried about is an upper bound. If if we're adding up, let's say if we have an array of like end values, we're adding some positive integer, and we're scanning it for the largest, that's going to take n comparisons. So that grows like n. So we double the data size, we double the number of comparisons. So that's really what we care about. What is what function it gives the best upper bound estimate? Okay, and then let's say we're searching through an n by n array, a two-dimensional array, and we're trying to find the smallest or the biggest. Then as n grows, well, if it's n by n, there's n squared elements in it. So as n grows, the number of comparisons grows by, if it's n by n, there's n squared comparisons. So you double the data size, the number of comparisons grows like 4. So we want to keep that exponent down as small as possible. Okay, so hopefully everyone can see this. Okay, so, and this is online, complexity second lecture. Okay, so we're going to talk about estimating operations for a loop, and maybe a couple of best case and worst case scenarios. And so suppose we have an inner product. Let's just look at this simple example. We have an inner product, and if you've taken calculus, not calculus, well, actually, I guess third semester calculus, but if you've taken physics or linear algebra, let's say if you have two arrays, each of length n, so the inner product would be you multiply the elements component-wise and then add them together. That's a really common operation in linear algebra, and it takes n multiplications and n plus 1 additions. Okay, so if you add up all the multiplications and additions, n multiplications and n minus 1 additions, there's 2n minus 1 arithmetic operations. And we don't really care about that minus 1. So for a large n, that minus 1 isn't meaningful. Like if you have $100,000 and you lose one of them, well, it's not really, maybe you don't notice it, but if you have like $10 and you lose $1, well, you just lost 10% of your money. Okay, so but as n gets big, that minus 1 is the lowest order term is negligible. So we just drop all the lower order terms, and we don't care about the coefficient. When we do this big O estimate, it actually would be wrong to include the coefficient. We just want some function of n. Okay, so in this case, 2n minus 1 operations. The big O estimate is big O of n, order n. It grows like n. You double. Okay, so which is linear. You double the data size, you roughly double the number of arithmetic operations. Not exactly. So if n is 50,000, there's almost 100,000 operations. N doubles to 100,000, well, then it's about 200,000 operations. Double the size of n, double the number of operations. That's the nice thing about linear. The number of operations grows, like the data size. Okay, so here's another one. So let's just look at this loop right here, that very simple loop. And all I'm doing, it's not doing anything meaningful. Every time I enter that loop, I'm just adding one to sum. And okay, but we don't care so much about that. But let's just see if we can get an exact number of operations and then an estimate. Well, assigning 0 to sum, that's an operation, that's an assignment operation. In the for loop, assigning 1 to I, that's an operation. That's done exactly one time. So assign 0 to sum one time, assign 1 to I one time. Okay, now if you look at that Boolean expression, I less than n, it executes n times. It's true when I goes from 1 to n minus 1, but there's one final evaluation where it has to be false at some point, or else the loop goes on and on forever. So when I is equal to n, when I equals n, then it stops. But basically, it's going to iterate. We're going to evaluate I less than n from I equal to 1 to I equal to n. So that evaluating the Boolean expression is n operations, and that I plus plus, that loop actually iterates n minus 1 times. It doesn't iterate when I is equal to n. So I plus plus executes, increase I by 1, executes n minus 1 times. And we execute sum plus plus, because there's n minus 1 times, because there's n minus 1 iterations. So now let's add them all together. 1 plus 1 plus n minus 1 plus n minus 1. And that all adds up to the minus 1s cancel the plus 1s, and we get 3n. So that loop takes exactly 3n operations, where if we include, and the operations are assignment, comparison, or addition. Okay, but the big O estimate is n. We'd say that this grows like n, so we'd go order n. So we would just drop that coefficient, so the exact number is 3n, but when we talk about the big O estimate, we just say, oh, it grows like n, or it's like order n. Once again, it's linear. You double the number, you double the size of n, you double the number of operations. Now here's another one. It almost looks like the example 3. It looks like the previous example, only now look, we're incrementing I by 2. Okay, so assigning 0 to sum is one operation. Assigning 1 to I is one operation. Okay, now we're going to evaluate I less than n over 2 plus 1 times. So it's going to be true n over 2 times. And finally, there's going to be one operation, there's going to be one comparison where it's false. So that's what I'm saying, that Boolean expression I less than n is evaluated n over 2 plus 1 times. And then we increase I by 2, n over 2 times, right? Because we're going 1, 3, 5. And sum plus plus, there's n over 2 iterations. So once again, let's just add these up. 1 plus 1 plus n over 2 plus 1 plus n over 2 plus n over 2. And if we add that all up, we get 3n over 2 plus 3. Okay, so we drop the lowest order term. Now when we're doing that big O estimate, drop the lowest order term of 3 and don't write the coefficient, right? So we lose the coefficient that's multiplying n, which is 3/2. And we also just get rid of that, that lower order term of 3. So the big O estimate is n. Okay, so this example is a lot more fun. Okay, so now we're going to show that the answer is that this takes log n operations. This grows like log of n. And notice what we're doing is that we're doubling the size of I each time. So it's going 1, 4, no, 1, I starts out at 1, and it's going 1, 2, 4, 8, 16, and so forth. Okay, so, and each time we add 1 to sum. Okay, so the value of the counter variable I, we doubles every time. So the first time is 1, which is 2 to the 0. The second time is 2, which is 2 to the first, then 2 squared, 2 cubed, 2 to the fourth. And you see it's the exponent, the number of iterations. The exponent can basically tell us the number of iterations. The exponent, the number of iterations is equal to the exponent plus 1. So when I equals 16, we're actually on the 4 plus 1 iteration, which is 5. So when I was 1, the exponent is 0. So we're on 0 plus 1. The iteration number is 0 plus 1. So we just add 1 to that exponent. It tells us which iteration, which iteration we're on. Okay, and then, so the number of iterations is about, I have it exactly there. It's the ceiling of log base 2 of n, but it grows like n. And it grows like log 2 of n, log base 2 of n. Okay, so because like when I is 16, the exponent is 4. So the exponent is really 1 less than the iteration number. So the number of iterations is about log base 2 of n. So remember the exponent is just a logarithm, right? Log base 2 of 16 is 4. Log base 2 of 8 is 3, and so forth. So let's just see if we can estimate the number of operations. Okay, so it's about log of n iterations. Now if I'm assuming n is a perfect multiple of 2, or a perfect power of 2, like 8 or 16 or something like that. So one operation to assign sum to 0, 0 to sum, another operation to assign 1 to I, that just happened each one time. Okay, I less than n, because we're doubling I each time, it's about log n plus 1, right? So eventually, eventually I less than has to be false, so that's what when I go log n plus 1. So we're going to evaluate I, so when I is less than n, that occurs about log n times. And then the adding 1 is when I is greater or equal to n. And then we do that assignment, I is assigned 2 times I, about log n times, and the addition, sum plus plus, concerns about log n times. So it's roughly, we add those all up. We get 1 plus 1 plus log n plus 1 plus log n plus log n. It's like the other one. Instead of 3n plus 3, it's 3 times log of n plus 3. And so the big O estimate, we drop the lowest order term of 3, and we drop the coefficient. So we say that that sum there, this sum right there, the one where the I is doubling every time, we're saying that the number of operations grows like log of n, right? So if we double it, well, the log grows slowly. So if n is 1,000, that's about 10, and I'm going log base 2. If n is 1,000, then the log is about 10. If you double that from 1,000 to 2,000, then the log would be 11. So you double the data size, the number of operation grows like about 1. Okay. You go from 1,000, you square, you go from 1,000 to 1,000,000. Well, we go from 10 operations to about 20 operations. Yeah, because about 2 to the 20th is about 1,000,000. Okay, so here's one we can look at the best and worst case. Sometimes sometimes the best case is the same as the worst case. They're not any different. And for some, really complex algorithms, finding the best case can be difficult. So we're just going to search through an array, and if we find the key, we stop iterating. Kind of like we did, earlier in the year. So I don't want to keep it. No need to keep iterating once you know that the key is actually in your array. So the best case is 1. Let's say we have this array of size 1,000,000, and the very first element is let's say we're looking for 4. It's an integer array, and element 0 stores a 4. Oh, we got lucky. It's just one comparison. So the best case when we're searching for a key in an array is 1. It's just one operation. If we're lucky, we find the key right away. Okay, but let's say we never find, the worst case is that we have to look through the entire array. And the element is near the end or it doesn't exist at all in the array. So this is what we did at the beginning of the year. Define a Boolean variable called flag, and I assign it false. So that's one operation. Assigning 0 to the index or the counter variable, that's another operation. That's 2. And then we're going to evaluate while I is less than arr.length, and then we're going to evaluate not flag. Okay, so I less than arr.length will occur n plus 1 times. So if we look through the entire array and the element's not there, then you're going to eventually evaluate compare I and arr.length. Okay, and then you won't actually evaluate not flag in that case. So it's n plus, so that the Boolean expression in the while loop in the worst case scenario occurs n plus 1 plus n times. Okay, let's say we're actually in the loop. Okay, so first we compare ARR of I and key. That's the comparison, is key equal to ARR of I. And then we assign a value to flag. So that middle statement, the one where we go flag is assigned, ARR of I is compared to key. That's actually 2 n operations, 1 assignment and 1 comparison. And then we increase the counter variable, and that occurs n times in the worst case scenario. So in the worst case, it's 1 plus 1 plus n plus 1 plus n, and then 2n for the, that assigning, comparing ARI to key and then assigning to flag, and then n for I plus plus, and we get, I think that's, what is it? It's, how many is that? So it's 1 plus 1 plus 1 is 3, and I think there's 5 n's there. So in the worst case, it's about 5n plus 3 operations, but again, the order, the big O notation is just n. We drop the 3 and we drop the 5. We drop the lower order term of 3. We don't care about that. and we don't use a coefficient. And in the best case, we still assign false to flag, still assign 0 to I, so that's 2. Okay, so let's say, I'm assuming that the array has at least more than one value. So we do that first iteration, and it turns out, oh, ARR0 has our key. So there's an operation, and we assign that to flag. There's another operation. So that's 2, right? And then we do I++, and that should just be, oh, maybe I have one more than I need to. Good. 1 plus 1. Oh, no, let's see then plus, no, 2 plus 2 plus, I think that last 2 should just be, not that big a deal. I think that last 2 should just be plus 1. Yeah, I think that's incrementing I by 1. Okay, then we do oh, no, I'm right, students, I'm right. Just the way I did this, I just kind of got them out of order. That last plus 1 is increasing the I plus in the iteration. Okay, so assign false to flag, that's 1. Assign 0 to I, that's 1. The comparison, evaluating I less than AR.length and evaluating not flag, that's 2. Doing a flag is assigned ARR0 equals key, that's another 2. And then plus 1 for the I++, and I put that at the end. And then you go back to the while loop and you evaluate that Boolean expression. Well, I less than ARR.length will be true because I'm assuming ARR length is bigger than 1, and that flag will be false, so you'll stop. Yeah, so it's 9 operations, so not that exciting. But it's a constant number of operations. If the very first element of the array stores the key, it's a constant number of operations. It's always 9 in this case, for this code. Okay, so using the terminology that we used last time, the number of operations for the while loop that we just looked at, the one that's searching for a key, well, it's order. Okay, so we said that it's the big O notation. So the exact number is 5n plus 3. So the big O notation is n. And the best case scenario is a constant. So we just say 1. So when it's when an algorithm uses, requires a constant number of operations, it doesn't depend on the data size at all. Like, oh, I'm searching the key that we're looking for is the first element. The array could be 100 elements or 1,000,000 elements. It's always 9. So in the number of operations is a constant. We say the order grows. The best, if it's the best case, we'd say order growth is 1, big O of 1. And if it's the best case, if it's the worst case scenario, that's the big O notation. We'd say order growth is 1. In this case, we're saying that the best case is a constant number of operations. So that omega key is the symbol for best case, that estimates the best case. It's a function that represents is a lower bound. So in this case, we say that while loop is omega of 1. So it takes so in the best case scenario, it takes at least 1 operation or a constant number of operations. And in the worst case scenario, it's some multiple of n operations. So students, okay, so now, and this is probably something you're going to see in your quizzes. We're not going to look at we're not really going to try to find the exact number. We're just going to, for these loops, we just want to find the order of growth. Okay, so let's just see. So one thing you may have noticed is that the order of growth depends a lot on the incrementer. So if it's a constant number of operations inside the loop, and if you look at all these few problems that we've done, the number of operations is like here, the number of operations is just 1. So the number of operations is not a function of n. So the number of operations inside the loop is a constant. Like here, it's just sum plus plus. We're adding, increasing I by 2. So in all of them, we're doing like sum plus plus. So it's either 1 or 2 operations per iteration. So, but it's always the same number of operations per iteration. When that's the case, the order of growth, that big O notation, depends on the incrementer. Like when we double I every time, and we had a constant number of operations inside the loop, the order of growth was log of n. Okay, so when the number of operations increased by like a constant, that's what we call an arithmetic progression. I is first 1, then 3, then 5. You just keep adding 2 on every time. The order of growth is n. So really, it's that incrementer when and so for our problems, at least for now, the number of operations per iteration is a constant. It's that incrementer that really tells us everything. Okay, so let's just go back to the main part of this problem right here. So let's estimate, let's look at nested loops. So here's a very simple nested loop. And again, not necessarily that interesting. Okay, so we're starting I at 0. And so we're going to do about n iterations. So we just multiply the number of iterations of each loop. So we have nested loops. So the outer loop is about n iterations. It's really, yeah, it's n iterations. And we know that it actually, I less than n will actually execute, well, in this case, we'd actually execute n plus 2 times. So, because this is going to execute, the Boolean expression executes n times when it's true, and then one more time when it's false. We're going from 0 to n minus 1. But it's about n iterations for the outer loop, n iterations for the inner loop. And again, what tells us the number of iterations? It's the incrementer. For each case, we're starting at 0 and we're incrementing by a constant number, in this case, 1. So you just multiply that n by n together and you get n squared. So the loop is about order n squared. So you double the size of n, the number of iteration grows like 4, right? Okay, so if n is 10, oh, it's about 100 iterations, 10 times 10. Now if we double that to 400, well, 20 times 20 is 400. So if n goes from 10 to 20, the number of iteration goes from 100 to 400, grows like 4. The quantity 2n squared is 4n squared. Okay, but the important thing is, in analyzing these loops, is look at the counter variable. Is it I++? Is it I equals assigned I plus 2? That's really the important thing. Oh, so students. So here's one of our favorite examples, example 7. Okay, and oh, students, I corrected some errors last night. I realized as I was speaking, I bet I didn't correct this error. I will correct this after class, okay? Do you see how I have that j is assigned 0? It really should be assigned 1. If I start j out at 0 and I multiply by 2, it's just going to stay at 0. Yeah, it really should be j equal to 1, and I'll fix that. But let's just pretend it's j equal, it starts at 1 right now. It's initialized to 1. Again, it's a constant number of iteration, a constant number of operations in every iteration. We're just increasing sum by 1. Okay, so the outer loop, it's about n iterations because it's growing arithmetically. It's growing by a constant. 1. We start at 1, and then to get the next value of I, we just add a constant. 1, 2, 3. Okay, if in the inner loop, to get the next value of j, we multiply by a constant. So the j is growing geometrically. You know, if j starts out at 1, it's 1, 2, 4, 8, 16, 32, and so forth. Okay, so the outer loop has about n iterations, and the inner loop has about log of n iterations, in this case log base 2. And you just multiply them together, and the big O estimate is about n times log of n, or I wrote it there. The loop is big O n times log n. So that's better than n squared because log of n grows slowly. So that's called linear arithmetic. I think I spelled that right. And is this the one? Yeah, so this one's fine. Okay, so now students, look at this one right here. In this case, we have in each case, so once again, we have a problem where the number of iterations, for every iteration, it's a constant number of operations. So all we do is look at the counter variable. Okay, the outer one, we increase by 1. The inner one, well, we start at n and we go down to 1, but we're decreasing by 2. But again, it's each kit for I and j are both changing arithmetically. We either add or subtract a constant. Okay, so there's about n iterations for the outer loop, and about n over 2 iterations for the inner loop because we start at n and then n minus 2 and then n minus 4. Multiply them together. So the number of iterations is about n squared over 2. And remember what we said before? Well, when we talk about the big O estimate, we drop the coefficient. So the loop is about order n squared. You double n, the number of iterations grows like 4. Oh, so here's a fun, this is our last one. And once again, I've got to change those two examples. I should start out at 1, because I equals 2 times I will always stay at 0. But in this case, notice how in this case, we're not, to get to the next value of I or the next value of J, we're multiplying by a constant. So they're growing, I and J are growing geometrically. So it's like 1, 3, 9, 27, 81, 243, blah, blah, blah. I don't know after that. And then the I, if I start at 1, it would be 1, 2, 4, 8, 16. Okay, but when the counter variable is multiplied by a constant, or we get the, or divided by a constant, we say there's about log n iterations. So the outer one has about log of n, and the inner one has about log of n. So we'll just multiply them together. And that correct notation, you put the superscript above the G. And that's the correct notation. That's the notation. If you take, I assume, I can't remember if you do that in the pre-algebra courses, but you certainly do it in calculus, which is not actually a requirement for this course. But you know, f of n squared, it would be f, and then the superscript would be above the f. So you're talking about squaring a function, you put the superscript above the name of the function. So that's why I have the 2 above the log. Okay, so and one last thing, so I don't really care about, notice I'm not actually saying what the base is. Yeah, so when I'm talking about big O notation, and we're saying, oh, the order of growth grows like log of n. So what the base actually is not important, okay? Because all logs are, one log is a multiple of another. So okay, so there's that famous formula that the log of x base a is equal to log of x base b divided by log of a base b, where a and b are positive constants. So it turns out that the log of a is just some constant times, the log of x base a is a constant times the log of x base b. So let's say one log is just a multiple of the other. So it doesn't really matter. When we're talking about order of growth and we're just dropping the constants, we don't really care what the base is. But usually when people talk about the base, when they're talking about computer science, it's often base 2, maybe sometimes base 10. So I'm going to stop sharing this. And I think I'm still the only participant. Maybe I'll ask myself a question. Well, what Professor, what should we share next? Okay, how about, why don't we share some slides on recursion? Any objection to that? Okay, so I could tell a few jokes now, and if you're really listening, you'd have to listen. And I guess you could fast forward, but I will go to, let's go back here. Okay, this is tabbed. Okay, so there's actually 2 PowerPoint slides for this lecture. And I'm trying to follow the book, like those individual chapters in the book. We're talking about recursion. Okay, so in recursion, you may have, I certainly do not talk about this in Math 130. A recursive method is just a method that calls itself. I changed some of these slides a little bit yesterday after I gave my previous lecture. Yeah, so a recursive method calls itself, can call itself, and a recursive method or recursive algorithm has to have 2 critical features. It converts a problem into a similar but smaller problem. And it has to have some kind of stopping condition. When the problem gets so small, you just stop. Okay, so let's look at the famous factorial function, which is just the product of, the factorial event is just the product of the 1 times 2 all the way up to n. So like 4 factorial would be 1 times 2 times 3 times 4, which would be 24. Okay, so then notice that factorial of n is n times factorial of n minus 1. So 3 factorial turns out to be 6, right? 1 times 2 times 3. But if I want 4 factorial, I don't have to start from the beginning, 1 times 2 times 3. I've already calculated 3 factorial is 6. 4 factorial is 6 times 4, which is 24. If I want to calculate 5 factorial, I just take 4 factorial, which has already been calculated, that's 24, multiplied by 5, and I get 120. So 5 factorial is 120. So n factorial, you just take the answer for n minus 1 factorial and you multiply it by n and you get n factorial. But we need a base case. If factorial of 1 is just said to be factorial of 1 factorial is just we just define it as 1. So you start at 1, you just say 1 factorial is 1. And then 2 factorial would be 2 times 1 factorial, which is 2. And then 3 factorial is 3 times 2 factorial, which is 3 times 2, which is 6. Right? And 4 factorial is 4 times 3 factorial, which is 4 times 6, which is 24. This is kind of bad. I wish I kind of had a whiteboard at this point. But anyway, factorial of n is n times fact minus 1. So you can see there at the bottom of slide 4, that fact function is calling itself. But instead of passing it n, we're passing it n minus 1. And that's what I mean. We're making the problem smaller. Right? So we're turning factorial of n into a slightly easier problem. Okay, so if I had 7 factorial, I'd say, well, let's turn that into a slightly easier problem. It's 7 times factorial of 6. I mean, factorial of 6 is a little bit easier than factorial of 7. So, but, I mean, you wouldn't use recursion really for factorials. It's just a great example, though. Now, I think I missed something here. Okay, so here's some actual Java code for factorial. Thought I had it. Yeah, right here. Okay, so there's the base case. If n is 1, that's the base case. Just return 1. Otherwise, return n times factorial of n minus 1. So when I write recursive methods, I do use more than one return. It's the only time in this course you'll see my code have more than one return. Now, if I'm using code from the book, I'm going to say code that I wrote. If I'm using someone else's code and it has more than one return, I'm not going to change it. So my code, the ones that I write for this course, will have one return if they're non-recursive and multiple returns if they're recursive. And the reason I don't insist on one return for recursive methods, it just, I think it just is, I think it just, if you're not used to recursive methods, it just makes it harder to read. Okay, so I like that, if you're at the base case, return. Okay, just kind of emphasizes that you're at a base case. Okay, so now let's recursion to compute the famous Fibonacci numbers. So the Fibonacci sequence is 0, 1, 1, 2, 3, 5, 8, blah, blah. I think this is used in nature somehow. I had a student who was like horticulture, and he explained it to me one time. I think now I've forgotten though. But anyway, it was very interesting what he told me though. So let's define f of 0. We just say the first Fibonacci number is 0. And the second Fibonacci number is 1. And then you just take the two, to get the next Fibonacci number, you just add the previous two. So f of n is f of n minus 1 plus f of n minus 2. So like, how do we get the third Fibonacci number? It's 0 plus 1, we get 1. So now the first three Fibonacci numbers are 0, 1, and 1. How do we get the next one? 1 plus 1 is 2. And then how do we get 3? Well, the two previous ones are 1 and 2, so 1 plus 2 equals 3, and so forth. And so we can actually write a recursive, I'm not saying it's a great code, but here's it, but this is definitely, if you look at this formula right here, this recursive formula, we're saying f of n depends on f of n minus 1. If you know Fibonacci for n minus 1, and you know the Fibonacci value for n minus 2, you know the Fibonacci value for n. Okay. So that's what I'm saying. You can convert the computation of the nth Fibonacci number by using the n minus 1 and n minus 2 Fibonacci number. So here's some code. Okay, so here's your base case. If n is 0 or n is 1, just return n. That's your base case. Otherwise, just return Fibonacci, you put an n minus 1 in, and Fibonacci, you put an n minus 2 in. And I don't think this is a good way to calculate the Fibonacci sequence, but it's a good example. Okay, so we could use recursion for greatest common divisor. I'm not going to go into the amount of detail I used to do, but if you want the greatest common divisor in A and 0, well, the greatest common divisor is A because everything is a factor of 0. So we're looking for the greatest divisor of two numbers, and every positive integer except for 0, is a divisor of 0. So let's say A is positive, then A is a divisor of 0. So the greatest common divisor of A and 0 is A. So the base case for greatest common divisor, so we want the greatest common divisor of some positive number A and 0. The answer is A. A is equal to 1 times A, and 0 is equal to 0 times A. Okay, so the greatest common divisor of A and 0 is A. So that's our base case. And now we're saying the greatest common divisor of A and B is the greatest common divisor of B and A modulus B. Okay, so we're actually making it a smaller problem because that eventually that A minus B is going to will go to 0. So look, here's an example. Now I know you can do this go online into Google and it gives you the answer immediately, but let's say, we didn't have Google, we just had our calculator, whatever. Okay, but the greatest common divisor of 7,480 and 612, right? So we replace the first argument with the second. So that's equal to the greatest common divisor of 612, and the second argument is 7,480 modulus 612, which turns out to be 136. So it's not really obvious, but the greatest common divisor of 7,480 and 612 is equal to the greatest common divisor of 612 and 136. You see how we turn it into a smaller problem? And once again, replace the larger with the smaller. So the next time it's the greatest common divisor of 136 and 612 modulus 136. So we eventually get to greatest common divisor of 136 and 68. And it turns out 136 is a multiple of 68. So you do it one more step. And eventually you get to greatest common divisor of 68 and 0. And the answer is 68. So this is called, I forgot whose algorithm this is. It's off the top of my head. I should know. Is it Fermat's? I can't remember now. Okay, so, but it's really very fast. You just take a lot of modules and it's, eventually you keep doing this. Eventually the second argument is 0. And then the first argument is the greatest common divisor. Okay, so let's look at what we're really here for. Okay, so I don't do as many, I used to do a lot more. If I was in the classroom, you'd probably do more recursive methods, but let's look at the one we have in the book. And last time we looked at binary search. Remember what binary search does. It starts with a sorted array of integers. And we look at, because it's sorted, if we're looking for a key, we just start right in the middle. Instead of going linearly, we start at position 0, start in the middle. We can do that because it's sorted. And if let's say the middle, let's say the name of the array is numbers. If numbers of mid is greater than the key, then everything to the right will be greater than the key. We can rule it everything to the right because it's sorted. Like let's say we're looking for 10 and the middle one is 20. Well, 20 is greater than 10 and all the elements to the right of 20 will be greater than 20. So that means we just have to look to the left. So the thing about binary search, it cuts in half the number of elements that we must inspect when we're trying to find this key. So if we start at 16, and then the next time around, we only have to consider maybe about 8, and then 4, and then 2, and then 1. And then we either have the key is either in the array or it's not in the array. But in each case, we're cutting in half the number of positions under consideration. So in this case, numbers is the name of the sorted array. Okay, so we're going to look in positions from low to high because sometimes we call this method, we're not looking at every, sometimes we're just looking at part of the array. So the part of the array that we're looking at, the lowest index is low and the highest index is high. So initially low is 0, right? That's the smallest value. And the highest value the initial value of high is numbers.length minus 1. So we look at the entire array. Let key be the number we're trying to find. And then we look at numbers, then the middle is the middle index. So we see is numbers of mid the key equal to the key that we're looking for? So, have we actually found the key? Then we're done. We return -1 if the key is not stored in the array. So let's just look at this this is pseudocode that's actually in the Xi book. Okay, so we're going to notice students, when you look at this code, binary search calls binary search. That's what makes it recursive. If you don't see that, it's not recursive. So do you see how we call it binary search twice, or it's in an if statement. So we have this if-else statement. but there's two places where binary search calls itself. That's what makes it recursive. And then remember, to be a good recursive method, we have to have a stopping condition, and we have to make the problem smaller. So the first time low is 0 and high is like numbers minus 1, the index of the very last value. And if low is greater than high, that means we have no more elements left in the array. So if low is greater than high, turn -1. That's our base case. We're done. We've looked through the entire array. We've considered the entire array. The key is not there. Return -1. Otherwise, let's take the average of the low and high, the low index and the high index, and divide by 2. And that gives us the middle index. So if the value stored at the middle index is less than the key, and that means that everything to the left of mid is less than the key because it's sorted. Look to the right. So if numbers of mid is less than key, so call binary search again, but we're only going to consider elements of the array to the left of mid. So if numbers of mid is less than key, we call binary search, we pass in the same array, but now the lowest index we're going to look at is 1 right after mid, which is mid plus 1. We go all the way up to high, right? Because if numbers of mid is less than key, we just look at the remaining elements that are to the left of mid. Okay, so then, now let's say numbers of mid is greater than key. Okay, so then we would look to the left. If numbers of mid is greater than key, and everything to the right is greater than key. So let's just look to the left. So we call binary search again with the same array. We're not going to change the value of our low, but our high changes to mid minus 1. So if numbers of mid is greater than key, now we'll just look in from positions low to mid minus 1. I know when you hear me, and eventually you just return mid. Okay, so so return mid if numbers of mid is equal to the key. So let's just look at a real example here, because this is me saying, I use the variables, it gets kind of abstract. Okay, so students, let's say we have this array here. So so this array has 9 values. It's sorted 1, 8, 19, 20, 45, 56, 72, 80, 100. There's 9 values in there. The lowest index is 0, and the greatest index is 8. The name of the array is numbers. And let's say we want to see if 56 is in the array. So we're going to write computer code to determine if 56 is in the array. Okay, so we call binary search, and remember, we start in the middle. We calculate the middle index, which is just the average of the low and the high. So mid is 4. Numbers of 4 is 45. 45 is less than 56. Right, so 45 is less than 56. So everything to the left of 45 is less than 56 because it's sorted. So look to the right of position 4. So the next time we call binary search, the low changes to mid plus 1. So each time you call binary search, you're either changing low or high. Okay, so if we look to the right, that low turns into mid plus 1. And if we look to the left, that high turns into mid minus 1. Because in this case, we're going to look to the right. We're going to look to the right of position 4. So we're going to go from 5 to 8. We're going to look for element 56 in positions 5 through 8. So we average 5 and 8, and we get 13. I mean 6. The average is 6. So now we're going to look at, is 56 in position 6? Well, position 6 is 72, and that's greater than 56. So everything to the right of 72 will also be greater than 56. So now we look to the left of position 6. So now we're going to go from low, so our new high is going to be mid minus 1. 6 minus 1 is 5. So the last time we call binary search, we're passing in the array, right? So low was 5 in the second call. And now our high is going to be mid minus 1. So it's going to be 6 minus 1, which is also 5. So in this case, the low and the high are the same. They're both 5. So you take the average of the low and the high, and you get 5. Numbers of 5 turns out to be 56, so you return 5. And you do about, because we're cutting it in half every time, there's about log n column. We're going to talk more about that next time, how to estimate give an estimate for the runtime of a recursive algorithm. But in this case, you're cutting in half the array. The number of elements under consideration in the array is cut in half each time. So if it was 16, it'd be like 16, 8, 4, 2, 1. So yeah, so there, so it's actually about log n, log base 2n iterations. So I'm going to stop sharing, and I'm going to stop the recording.